do quickly. Okay, let me hide the video. Okay, yeah. So I want to just introduce some of the work that my lab does. It's generally broken down into three categories. So one is in terms of optimization of urban mobility fleets. And this can be a range of different topic areas. As you can see here, some of it is related to service region design for different mobility services, but some of it is like electric car sharing operations, modular platooning, emergency vehicles, so on and so forth. We also do work with looking at just multimodal transportation systems, market evaluation and analysis. Looking at market design, platform design, for these kind of multimodal settings, mobility as a service types of settings. And we also do work with system modeling at the city scale. So modeling, learning, monitoring, also considering like deployment of projects. So those are kind of like the three areas that my lab focuses on. What I'll talk about today really hinges upon emerging technologies. The title I mentioned is dealing with transit network design. But I want to start from emerging technologies because we're really seeing an explosion of different types of services that arise from these emerging technologies, right? So we're seeing services like ride-hail, microtransit, ride pooling, vehicle sharing, micromobility, and you can identify variants of all of these services based on different technologies, like automated vehicles, electric vehicles, urban air mobility modes, and different types of operations as well for different applications. What you see on this slide, this is the evolution of some of the micromobility in the last few years. This is, and the one above is the ride pooling market in 2023, which you can see there's a lot of tremendous growth in these different markets. My work pertains to these topic areas because there's a lot of, as we implement different types of mobility services, there are a lot of risks. So one of the challenges is trying to make sure we get them right, because oftentimes when they do fail, they end up becoming much more highly visible. And so there's a need to really try to better understand how these services operate. Right, so I like to share like this mobility graveyard with students just to get show them that it's not always about having successes. It's also about learning from the mistakes, and sometimes these mistakes, or it might not even be in your control. Right, these might be challenges that arise because there might be just circumstances that make it prohibitive to operate these types of services. So trying to understand all that. And so the motivation there kind of leads to this area of research called this sequential decision analytics. Because a lot of those types of services, they tend to be a little bit more dynamic. There's a lot more uncertainty involved in them, right? So particularly for the on-demand types of services, although for this talk today, I will actually focus more on fixed route types of services and planning under uncertainty in the long term. But I do want to highlight that under this branch of research, there's a lot of interest in being able to dynamically allocate resources. So considering things like dynamic routing, dynamic pricing, dispatch, or dynamically repositioning the fleets or sensors in the system. And all these different decisions that need to be made by operators and policymakers, they're fundamentally dealing with this common challenge of recognizing patterns from data to derive policies under uncertainty, right? And just to go into a little bit of this, I don't want to dwell too much on like the notation or the math. In fact, I'll go a little bit quicker past that. But ultimately, there are methods dealing with this, right, where you're basically looking at decisions over time and you're getting information in real time, making decisions where you might have to make some kind of projection into the future, and how your decisions at a current time might impact those decisions in the future, right? And one of the opportunities in these types of problems identified earlier on by other researchers is the opportunity to consider optimal learning. And optimal learning essentially involves the idea that you can, the decisions that you make now can explicitly consider the information that you can gain in the future, so that you can use that information to better improve your subsequent decisions in the future, right? So in that sense, you're explicitly accounting for that uncertainty in the future and trying to make your decisions to accommodate that in a way, maybe adding more exploration as opposed to just having exploitation, right? So for those very familiar with reinforcement learning, that's the quintessential characteristic of this field, right? And this is where we might observe opportunities to incorporate optimal learning into some more traditional transportation planning types of paradigms, and that's where I'm getting into this. Again, I'm not going to dwell on the notation, and in fact, I'll probably skip. There's one or two slides that I'll probably skip later on. So the topic of this is actually a working paper right now, currently under revision. It's called Sequential Transit Network Design with Optimal Learning under Correlated Beliefs. The concept of this is we're taking the classic transit network design problem and changing it to a sequential paradigm or incremental paradigm where we try to absorb information, and so that we can use that information to make our subsequent our decisions to exploit the improved information in subsequent decisions. And there's different types of learning mechanisms that can handle that. And one particular one explicitly considers correlated beliefs between the different options. And that's an advantage that we thought can be exploited, but we weren't sure how much that advantage actually is. And so in this study, we really try to quantify that with a series of experiments. Okay, so just to start off, I want to talk about what transit network design is, because maybe different people have different ideas about that, right? So the very basic model of transit network design, you're typically given some demand. It could be like point demand, it could be origin destination demand, and you're dealing with link operating costs and some kind of budget and your parameters, and you're outputting different routes, different stops, perhaps service frequency, right? So in terms of like the number of buses or trains in your fleet size to accommodate those routes, and this type of study, this work has a very long history. So there's even studies from like 1960s. I was debating whether to show that, but this one from the 1980s at least has some diagrams to kind of illustrate the general concept, right? So I thought this would be a good one to kind of show. But where you're given a test network, underlying network of where you want to design your transit routes to provide adequate service. And this is quite a challenging problem, right? Because the basis of this is essentially selecting different links or segments to provide service for, and you can really boil this down to basically a type of a knapsack problem, which is known to be NP complete, right? So these are challenging problems, but with transit network design problems, they're further even more complex, because you have these added decisions like frequency setting, or added constraints like continuity in the lines and segments. And there's further work in recent years that have tried to go beyond even those basic added complexities. So issues like having hyperpaths where people waiting for transit services might probabilistically be assigned to different lines, or integrating mode choice so that it's accounting for choosing transit over other modes, or having stochastic demand, right? So stochastic demand, in fact, that's kind of where we're heading towards here, right? So stochastic demand, and some work has been done on stochastic travel times as well. But let's focus on stochastic demand, why that is important. Right, so on the right-hand side here, I show, and sorry for the siren, sirens out here, this is New York City. So on the right-hand side, we see two different transit systems and their evolutions. And what you can see is essentially these transit services can take years or even decades in some cases to complete and to advance. Right, it's a very long-term process. So how can we rely on forecasting that makes a forecast of demand so that we can really build the right system to meet those demand needs. That's really the challenge, right? So in traditional transportation planning approach, there are well-defined ways to try to do this, and the state of practice essentially is just making point forecasts into the future, maybe 20, 30 years or even more into the future, to have some kind of deterministic demand setting that you target, from which you try to allocate funding to build out project investments. Right. Well, the problem becomes a little bit trickier when you're dealing with particularly emerging technologies, right? Because in those cases, oftentimes you don't really have forecast data available, right? You don't have initial data to really use to make these kinds of projections. You might be able to deploy some pilots to get some initial characteristic data, right? But you won't really be able to get a very good picture of how much everyone prefers transit, let's say, right? If it's dealing with an emerging technology type of transit technology, right? That's different from, let's say, if I wanted to build a bus system, we have a lot of public data sources, surveys that that really tell us, in New York City, for example, how even down to the census tract level, how people prefer to travel by different modes. But again, for emerging technologies, this is much less so available. And so this is where having a more adaptive approach might be beneficial, right? So we want to consider a sequential network design paradigm where we make incremental changes, right? So here is a snapshot in time where you have two different lines built out so far at a current time, and then you consider different alternative increments to further expand the system, right? And the idea here is that the opportunity here is you can be more flexible, right? So you can see how based on the new data that you obtain, how that would based on that new data, you might then adjust your decisions about where to set your routes, or what kind of fleet size you use, right? This could be very beneficial for the case where, like, if you ended up building out a fleet that was too large, or like using a technology that was much higher capacity, but you end up having much smaller ridership, you can adjust for that. The challenge, on the other hand, with this type of design is that the information that I get will end up being different between the left and the right, because building out that green line on the left versus building out the red line on the right would then get me new information that's different from those two different locations, right? And so this is where we're seeing like an opportunity to really make our decision such that we want to be able to incorporate the collected data from those incremental improvements in a way that's also intelligent, right? So we're not just trying to just use the current data and maybe project how our system will perform in the future, but also try to project how the system would acquire new data in the future. and use that into our current operations. Right, so that's the difference. So we're trying to look at a sequential network design problem where we are also adding some optimal learning mechanism. Okay, so the objectives of this research include first, designing a framework of sequential transit route design, one that allows us to incorporate these learning mechanisms. And it should be complex enough to at least be able to handle transfers, demand correlations that can translate from OD pairs to route level decisions. And it should still be simple enough to be able to compare different learning mechanisms without too much noise, right? Because we want to be able to try out different settings, different designs, and be able to make a conclusive decision about which approach might be more appropriate for this. We also then want to test this framework in both synthetic data setting as well as realistic data setting. Right. So for the realistic data setting, we want to test this on New York City data that we have, and the benchmark for this is to compare this against other operating policies or network design policies. Right. So a greedy one might be a lower bound one where we don't try to incorporate exploration or learning into the sequential network design. And an upper bound is one where maybe we can identify like a way of determining a best case value. And I'll talk more about that later on. So the framework here is, we can call the problem here a sequential segment level transit network design problem. It breaks down into essentially there's a route expansion that can be further broken into within each route. There's a segment extension, and even within each segment extension, we assume there might be multiple time steps in each epoch where learning can take place, where you can get observations and you can use those observations to gain information. As opposed to on the bottom where you make the assumption that all the demand is known in advance at a future point in time, and you just design a full system for that. Right, so we're trying to avoid that latter paradigm. And the underlying uncertainty here is that the OD demand is the uncertain random variable here. We don't know what the mean or covariance is, but as we gather more information, we can update our prior knowledge about those two parameters of the distributions, and so that over time we can try to explicitly incorporate ways of improving our understanding of that uncertainty. And if I'm given my time, I won't really be able to dive too deep into like the detailed mechanics or the notation. But if you have questions, feel free to email me afterwards, or also you can reach out to my my colleague, my former student at Seoul National University. Okay. So the way, as I mentioned here, is really an iterative process where we start with, we assume that the decision maker is able to collect existing data from a pilot, from which they can then prepare an initial prior, from which they iterative go through these loops where they go through route expansion, segment extension, and then there's these updates. Okay. And then for the learning mechanism, we experimented with 3 different types of learning models. So we considered multi-arm bandit, knowledge gradient, and knowledge gradient with correlated beliefs. The main difference is the multi-arm bandit assumes that we're dealing with independent arms. It's simple to implement, so that's one benefit of that. But and there's applications that in fact we worked with in prior studies. But the disadvantage is that it assumes all the options are independent of each other. Right? So there's no way of capturing the correlations between them. Knowledge gradient it's a little bit more advanced in that it's now more dealing explicitly with like a one-step look ahead of the decision impact on those distributions. Again, I'm skipping the notation. The main difference with the KGCB, with the correlated beliefs, is that it tries to incorporate the impacts of the new knowledge into the changes in the covariance matrix, and it's able to use that to quantify that difference in making those decisions. Right, so I'm going to skip this slide. So we tried testing this out with a synthetic example first. So we started with a 5x5 grid network. The blue network here, what you see is the example of like the true flow patterns from which we then hide it. And then we collect an example pilot service data set. So using the same pilot service data set, we run the 3 different learning mechanisms through that algorithm that I showed you earlier. Right. We run this for a number of different cases where some portion of the flows are assumed to be correlated and some are not. And we set certain standard deviations. And we can see that there are different patterns that arise. And we also note that the demand coverage for KGCB does outperform a little bit. It's a small example, but something that we started from just to show that there is some promise with this, right? So based on that, we expanded it further, right? So we conducted a second set of experiments, this time with more realistic data. We took New York City. We use travel survey data to kind of fill in, to create this kind of OD flow matrix as assumed assumed to be a ground truth of the how the OD matrix behaves, and then we set up again pilots to create initial belief of or prior of the different OD patterns. And then we test this under different scenario settings of low, medium, or high flow variance, as well as 5 different versions of each of those scenarios to see how it behaves. This is just to illustrate for the 5th scenario for the high variance, how the outcomes look. What we saw is MAB and KG tend to be pretty similar. There's some minor differences, but KGCB is a little bit more different, especially if you look in the Bronx area, right? And this is evident later too in the other results. It's indicative because the KG also doesn't consider correlated beliefs, and now by having the correlated beliefs, we're observing some different patterns. As I mentioned, the greedy policy is basically assuming we operate dynamically or sequentially, but we don't have exploration. And then for the upper bound, what we did is we implemented a policy that I had developed earlier with my former advisor. What this policy does is it takes randomized decisions over a dynamic setting and then fits those randomly determined decisions into a extreme value distribution, like Weibull distribution, so that we can derive the value of a maximum policy, the maximum value of a policy. And so using the Weibull distribution, for example, based on these random performances, we gather that a Weibull distribution would lie somewhere between this area, right? And so we can use that to kind of provide, here's an upper bound max value under this assumption, although it's possible that some of the results can exceed past some of the percentiles, right? And this is the result for comparing the 3 different learning policies against that greedy one, which is the yellow. Right, so the yellow highlight is the kind of serving as a lower bound. The reference policy, the CR policy, is kind of the upper bound. But the disadvantage of the CR policy is we don't actually know what the outcome decisions are. It's just providing a measure of how good potentially it can get. And we can see comparing between MAB, KG, and KGCB, KGCB is really the only one that even crosses some of the CR policy sometimes, right? We also noticed that this crossing happens more often under the low scenarios than the high scenarios. So it suggests that KGCB, considering correlated beliefs, does have an advantage, and that advantage tends to be better, or at least that tends to be a better compared to the reference policy in the case where the variance tends to be lower. Right. This is just marking them in a normalized setting. Right, and we also did t-tests to just compare against the three, and you can see comparing MAB with KG, they tend to be insignificant, but KGCB against the other two, it tends to outperform. All right, so to kind of conclude here, KGCB, we note that it does outperform the other two in both the synthetic and New York City experiments, and it suggests there's value in capturing correlations in the exploration, something to keep in mind, because with a lot of these kind of network problems, oftentimes we simplify and we assume that we don't have to capture it. KGCB also seems to have higher potential when the demand variance is lower. Right, so also something to keep in mind. Next steps with this work, we think there's opportunities to maybe develop like digital twin alongside an emerging mobility system deployment you can use it to provide decision support. We can have more sophisticated demand that is dependent on route characteristics. Here in this comparison in this study, we kept things very simple in terms of like demand coverage and things like that. And also maybe having more complex systems as well, like multimodal systems with on-demand service. So those are some next steps. Do I have like a minute or two to kind of just quickly blow through some other research?
Certainly, spend as much time that you need.
Okay, all right. So just really briefly, three other research topics that I'm working on that's kind of AI related, some more than others. But we have a recent study that's looking at also using deep learning, incorporating that into real options to use that for service region design and timing, right? So service region design is a issue, is a challenge. You can see like City Bike, microtransit via in Arlington. This is the mopeds in Revel system in New York City. Service regions change over time. They typically expand over time, and it's something that we want to try to help provide decision support. So we took real options methodology that I had developed earlier, and one of the challenges there was that it was very computationally expensive. So we tested out adding a recurrent neural network approach to train some of that to reduce the computation time. And we found that it was effective. So that's what this is reporting. Okay, so this is just an illustration of that. In another study where we've effectively developed an original data set of mode choices for the whole state of New York. And so this data set is using data that we got from an industry partner, Replica, which is an offshoot of Google that uses their smartphone data along with other data sources, combines that to provide synthetic population data across all of US. Right? So we took that data and because we have essentially all population data as opposed to a sample data, we changed our methodology, and the study, the reference at the bottom is the method, kind of like the core methodology that we use based on machine learning using inverse optimization to develop estimations for different agents. So here, each agent is an OD pair at the block group level. And using this, we can devise much more detailed information about how people travel for different population segments. It really opens up the ability to do equity analysis. We think so this is just some of the results we're able to get, like latent classes and so forth, and it does seem to fit observations. But just to illustrate like this, in this slide we see like different deployments of the model to integrate that with optimization. It tends to be more conducive for that because we end up having linear or quadratic programming depending on if you have multiple brands. So we're treating it as kind of like a assortment problem where we're trying to decide which service type to provide in different parts of the state, and we can see that having an objective that's revenue maximizing versus social welfare maximizing versus welfare disparity minimizing can have different effects. And you can see that by having some equity-based objective to reduce inequity, you can significantly improve welfare disparity. And this is a call for public agencies to consider subsidy in their programs. And then a third topic is looking at classifying different typologies of cities. So there are many cities around the world, right? And some earlier studies have tried to classify them into different types for earlier for 300 cities. So like auto heavy or bike friendly or congested or transit heavy. What we did was we took that data set and we took a natural language processing model using SentenceBERT and used that to extract data from Wikipedia to automatically train and test many more cities across around the world. Right? And this resulting data set is open source now. We have it shared, available here, but we expanded from this 300 city data set into what you see here. So this is a classification of different city types using that natural language processing model. Those are some of the studies that we also have, and now we're also embarking on looking at emergency vehicles, working with New York City Fire Department, and planning to incorporate some AI into helping them reduce response times. So that's a new project that we're starting up. Yeah, I'll stop here. I welcome any questions or feedback.
Well, thank you so much for sharing, a variety of transportation research. I'm really happy to share, many different perspectives that we can play with in the domain of transportation. So I have one question in the meeting chat that, hi, Joseph, thanks for your talk. I have a question. MAB essentially is a one-state MDP. In this link choice context, I think it should be a multi-state since you are moving in the network, and then the distribution of the reward is changing.
Yeah, that's true. So we kind of forced it onto this. So it's like a simplified model that we try to fit it into that case. We weren't expecting it to really work very well, but your suggestion is noted. Maybe we can consider incorporating that into some future work. Yeah, when we were designing this, we were kind of picking maybe as more of like a naive approach to see how well the other approaches might perform compared to that. So.
Sure. Does anybody have other questions? I do have some questions for him. But... Okay, Joe, I really enjoyed your talk. I learned a lot. I probably have more questions than the time that we have. So I probably need to, contact again to maybe have a joint lab seminar or something like that. The first question that I had was about the sequential, transit network design. So you consider the varying demand and then how the route choice is going to change and things like that. If we want to do something similar for the urban air mobility, it's not, demand is really critical, but also the amount of investment that needs to put in, including the power system and the real estate, acquisition and what have you, is going to be another, very interesting factor to incorporate. So do you think that the sequential transit network design can accommodate like multiple factors, whether it's dynamic or static?
That's a really good suggestion and idea. I think so. think that there's definitely an opportunity to apply it to that. I don't think you need to use that to capture all the uncertainty. I think you can also mix it up, maybe incorporate some robust optimization in there as well, and incorporate use that to consider maybe for the cost side of things, or you can maybe have it as multiple phases in the time where maybe the demand might be more frequent and the cost might be less frequent or something like that. But yeah, I think that's interesting. Yeah, so that would be, you know, one good application where we don't really have a lot of good data for that right now, right? So
Well,
over time we would collect more.
Yeah, discussion. All right. So much for my excitement, but I'm gonna move to the next next question. Minghao followed up on his question that I
Yeah.
think episodic MDP probably would be worth to take a look.
Yeah, and I thank them. Yeah, I definitely agree.
Yeah, and from Yuyo, thank you for can you go over your question? I don't have to do it for you, right?
Oh, thank you for the great presentation first. I have a question about the application of your framework. Would it be possible to apply your framework to assess the impact of some infrastructure change around it? Not the network of the transportation itself, but the infrastructure near the road segments. For example, would it be possible to see how would the traffic change when some mega shopping centers near a traffic node is constructed?
Yeah, I think definitely with the learning mechanism you can. I mean the framework that we have here is really more suited for like route design, which probably wouldn't make sense exactly for this, but I think the learning mechanisms out there for like sampling the traffic over time and deciding where to kind of sample the traffic, that could be applicable. But I think if it's very cheap and easy to implement the sensors and monitor over time like traffic conditions, then that problem might not exist, right? So you might just have steady information over time without having to decide. Like the main reason that we have this issue with the transit route design problem is that it's costly to implement. It takes time, and then once you do implement it, the configuration of your implementation impacts what you learn, and so that's where it makes more sense. But yeah, I think this could still be useful, but maybe in a different framework. Right, as an example, we have another study that I cited earlier where we looked at recommender system for like destinations. So like typically like services like Uber, they'll you use the phone to they'll pick you up, they'll drop you off where you want. But what happens if you don't know where you want to go? Like let's say you just want to go to a restaurant, and you want them to recommend some place to you, right? So like that kind of problem, it's a little bit trickier, but you can still incorporate learning mechanisms there to try to better understand what people prefer, and like incorporate that with the spatial temporal constraints to provide better suited advice, right? Recommendations. So yeah, I think there's a potential, but a different framework. Short answer.
Thank you.
Great. I think we covered every questions. Oh, yeah, purposely.
Yeah. First of all, Joe, thank you very much for your great presentation. Would you go back to one slide back?
Yeah.
I'm sorry, I didn't. Oh no, not this one. The one before. The disparity part.
The disparity.
Yeah. This one.
This one.
Yeah.
Okay. Yeah.
So I don't think I fully understood your presentation. I mean explanation. So
Yeah.
So this one actually the leftmost column, the vehicles the revenue, what does that mean? It means the traffic or the how many cars are actually allocated to for the service, or I'd like to understand the correlation between these three columns.
Yeah, thanks for pointing that out. Yeah, I raced through this really quickly. So basically what we did was we have a statewide set of mode choice models across the whole state. And then we integrated that into an optimization model for service region design of a hypothetical mobility service. So like the hypothetical mobility service, so we actually consider two hypothetical mobility services, but I think in this slide
Mobility service, you mean like shared car or the
like let's say like a ride pooling service
ride pooling,
implementing statewide. Where should we put it? How much of a fleet should we put at different locations? So it's making a statewide decision about where to allocate the fleet over time, not over time, but just under the given budget. So that's where the revenue and all that comes in.
I see.
So we try to make the decision based on different objectives of welfare maximizing or welfare disparity minimizing.
Okay, all right. Okay, thank you.
Mhm.
Thank you.
Thanks.
Joe, if I can add, since we talked about disparity and equity, JR is visiting me in December, JR Lijo, the Langone School. And we're going to have a small workshop on the assistive mobility options, including the wheelchairs and his own device for the blind and what have you. So do you think you also have some research related to this type of like a disabled or more the people with the difficulty with the physical mobility side?
Yeah, so I don't have research specifically to that topic, but my colleague Pan Osbe, their group definitely does. So they've been doing some really interesting work there. Testing. Yeah, so I think maybe you can check with him about that.
Oh, definitely. Yeah, I'll follow up. Thank you.
Oh, I have one more question, Joe.
Sure,
on the slide, right? This is the based on your simulated mobility service expansion.
Yeah.
Also thought about how this welfare disparity changes over the time and space wise. So spatial temporal dissipation perspective.
Yeah, we didn't consider that, but I think that would be pretty interesting. So essentially all the data here is based off of replica data from the year 2019. So I think what you're alluding to might be how if we collect data over time.
Yes, exactly. That's what we currently working on, because our previous work we tried to classify the regions in terms of the commercial gentrification based on Zukin's work. So the next job we currently working on is based on the traffic, and we call it human flow, how people move based on certain purposes, and try to look at the how these specific disparity across the multiple regions expanded throughout the time and the direction wise.
Yeah. Oh, that's pretty interesting. Yeah, I think that's the direction we want to take as well. Given like New York State is very interested.
Right. If you share the, it's just Yunjin said if we can have some kind of common place to share the data, not only Korea but also New York City, and then we have great platform for the value comparison, the purpose.
Yeah, absolutely. Yeah.
Okay. Thank you.
Great. Yeah.
Great. Well, thank you so much, Joe. It's very late in the evening, and I just
yeah, that's true.
Thank you enough for
same time zone.
It was such a wonderful talk. I learned a lot. I truly appreciate.
Thank you, again for having me, and it was my pleasure to present.
So I'll see you again in January. Okay.
Sounds good. All right. Take care. See you.
Good night. Bye.
Good night.
Bye.